Section 4 covers mostly how to combine the algebra rules that you know with trigonometric expressions and equations. We'll do things like simplify expressions that involve trigonometry, including factoring trigonometric expressions. We're going to learn three basic identities that can be used to help simplify trigonometric expressions. We'll solve some equations, and we'll learn how to do identities, which are proving trigonometric statements by working with one side only. There are three notation tricks that you should know for trig functions. First, even though functions normally have the input inside parentheses, for trigonometry those parentheses usually disappear. You still need to have an input variable. In other words, the theta must be there. Writing sine by itself doesn't make any sense. The second is that when you need to multiply trigonometric functions, normally the parentheses are dropped. Sine theta, cosine theta means take the angle, plug it into the sine function, take that same angle, plug it into the cosine function, and multiply those two results. And then lastly, if you need to square or use any kind of an exponent for a trig function, instead of having an outside parentheses, it's moved inside next to the function. This still means plug theta into the sine function, get a result, and then multiply that result by itself. There is one exception. If you need to find the reciprocal of a trig function, you cannot write it as sine -1 theta like the other exponent rules, because this means something different, which we'll get to later in the chapter. There are going to be 4 or 5 identities that are also going to help you out quite a bit. The first thing is that if we're working on a unit circle whose equation is x squared plus y squared equals 1, that's a circle with radius 1 centered at 0, 0. And if we define cosine theta as x and sine theta as y, this equation of a circle can be translated into sine squared plus cosine squared equals 1. In other words, the x is replaced with cosine theta, the y is replaced with sine theta, and we have what's called our first basic trigonometric identity. Since cosine is x and sine is y, and since all the other trig functions are based on the sine and cosine function, or based on x and y, we can write functions like tangent, which used to be defined as y over x in terms of sines and cosine. So in other words, tangent theta becomes y is sine theta, x is cosine theta, so I can rewrite tangent in terms of sines and cosines. And the same thing happens for the other three reciprocal functions. Secant was defined as 1 over x. X is the same thing as cosine theta, so now secant theta is 1 over cosine theta, cotangent theta is 1 over tangent theta, and cosecant theta is 1 over sine theta. All of these are worth memorizing because you'll be using them quite a bit. Okay, so to move on to some examples. The first two examples demonstrate how trigonometric algebra is the same as regular plain old algebra. This first expression, 2 cosine cubed theta sine squared theta minus 7 sine squared theta cosine cubed theta, can be rewritten in a much simpler form as 2c cubed s squared minus 7s squared c cubed. In other words, let's not worry about the trig functions. Let's just say cosine cubed is c cubed and sine squared is sine. In most cases, we'd recognize that these are like terms, even though they're in different orders. C cubed s squared is the same thing as c cubed s squared, so they're like terms. If I've got 2 minus 7, I wind up with a total of -5 c cubed s squared, and turning these back into their trig functions gives the answer of 2 cosine cubed theta sine squared theta. So just a quick example of how algebra with trig is the same thing as algebra without trig. This expression here doesn't have any like terms, but if I recognize that I have cotangent squared and cotangent and a term without a variable, I could rewrite this as c squared plus c minus 2. And traditionally we would factor that. 3c and c, and I think if I put the minus 2 here and a plus 1 there, I wind up with 3c squared plus 3c minus 2c, which is 1c, and then minus 2. So I factored an algebra expression, but c is really representing cotangent beta, so I'm going to rewrite my final answer as 3 cotangent beta minus 2 times cotangent beta plus 1. So again, the first two are just demonstrating that algebra with trig is no different than algebra without trig. The third example is our first simplification that was going to involve one of the most helpful tricks, and that's turn everything into sines and cosines. There are 6 trig functions, but the last 4 can be defined in terms of sine and cosine. So if I change cosecant into 1 over sine, and cotangent into cosine over sine, maybe this will simplify easier. Cosecant, as I said, is 1 over sine A plus 1 over cosine A plus cotangent A is the same thing as cosine A over sine A. Now it looks like we took a nice simple expression and made it much more, ugly or much more difficult. But I think seeing a sine A in the denominator here and a sine A in the denominator here means that if I multiply both top and bottom by sine A, everything in green here is just the number 1, and when I distribute this to the two terms in the top, one of the fractions disappear. Sine A times 1 over sine A produces a just plain old regular 1, and sine A times 1 is sine A. In the bottom, sine A times cosine A is sine A cosine A, plus sine A times the second fraction, the sine A's cancel, and I'm left with cosine A. And this still doesn't look too good, but if I look in the bottom and see a cosine A in the first term and a cosine A in the second term, I can factor that out. 1 plus sine A stays in the top. I'm going to factor out a cosine A, and I'm left with sine A plus 1. And now, two things in the top and bottom look identical. 1 plus sine A is the same thing as sine A plus 1, so I can cancel those two, and I'm left with 1 over cosine A, and 1 over cosine is same thing as secant A. So this expression, which started out as a fraction, boils down to a simple trig function, all because I turned everything into sines and cosines, used a fancy version of 1 that helped me get rid of two denominators, factored something out, and did some canceling. The final three examples are going to be more simplification of trigonometric functions. The first is one we've seen before. I'm given that cosine theta, or x, is -3/5, and I'm told that the angle is somewhere between pi and 3 pi over 2. In order to best figure out what that means, I'm going to draw a very small coordinate grid and say that theta greater than pi means bigger than 180, but less than 3 pi over 2 means less than 270. So I know I'm going to be working in quadrant 3 for my angle. I started here, and I'm going to wind up somewhere in quadrant 3, which means both ordered pairs, both parts of the ordered pair, both the x and y are going to be negative. So far that makes sense because cosine, which is x, is indeed -3/5. If I use my identity sine squared theta plus cosine squared theta equals 1, and if I substitute -3/5 for cosine, I have sine squared theta plus -3/5 squared equals 1. Sine squared theta plus 9/25 equals 1. Sine squared theta equals 1 minus 9/25. Well, 25/5 minus 9/25 is 16/25. And when I go to square root both sides, I wind up with sine theta equals plus or minus 4/5. I have a decision to make. How do I know whether the sine theta is positive or negative? I go back to my original restriction, and since I'm told theta is going to be in the third quadrant, I know that I'm going to pick the negative version and not the positive version. So I have sine theta, which is the y coordinate, is -4/5. The question said find all 6. I already know 2. Cosine is -3/5. Sine is -4/5. Tangent theta is defined as y over x, or sine over cosine, so I have -4/5 divided by -3/5. That's the same thing as -4/5 times 5/3 negative. The 5 in the denominator cancels with the 5 in the numerator. The two negatives cancel and become positive, and I have as final answer for tangent 4/3. The final three trig functions are just reciprocals of the first three, so since cosine theta was -3/5, secant theta is -5/3. The reciprocal of sine is cosecant. Cosecant theta is -5/4. And tangent theta has as its reciprocal cotangent of theta, which is 3/4. So I found all 6 trig functions. One was given. 2 we found using an identity sine squared plus cosine squared is 1. The third one used the fact that tangent is y over x. And then the last 3 are the reciprocals of the first 3. Okay, I think that's enough for day 1. We'll finish the next 2 examples in day 2.